Hi, these lecture slides constitute part 2 of set 1. In this presentation, you will learn about binary logic, variables, and functions. You will also learn logic operators, their symbols, and various representations of logic functions. Reference for further reading is shown in this slide here. Binary logic and variables. Binary logic is two-valued logic. That means it could be like true, false, yes, no, and say closed, open. Binary variables are variables that can take on two discrete values, 0 and 1. The value 0 implies false, no, open, etc. On the other hand, the value 1 implies true, yes, closed, etc. In the diagram, x equal to 0 indicates that the switch is open. That means there is no path for current to flow. On the other hand, x equals to 1 is for switch closed. That means there is a path for current to flow. Binary logic functions. Binary logic functions are functions or expressions of binary variables or other binary functions. They produce an output which is 0 or 1 depending on input values. A logic function can be defined using a truth table. The truth table indicates the value of the function for each possible input values. For example, here we have a truth table for two variables x and y. The left two columns indicate all possible input values that we can have. And the rightmost column f is the value of the function. Logic operators. Logic operations are needed to make logic functions and to manipulate them. There are three basic logic operators: and, or, and not. Symbols for logic operators are shown in this table. The leftmost column indicates logic operators: and, or, not. The next column indicates symbols used for those logic operators. For example, for logic operator AND, we use either dot or nothing. Here are the examples. So x dot y indicates x is ANDed with y, or we could simply write x, y without the dot. For logic operator OR, the symbol is this plus sign. So x plus y indicates x is ORed with y. For logic operator NOT, we use either prime or bar. For example, x prime or x bar. Operators have precedence in the order. First we evaluate brackets, then NOT, then AND, and then OR. The parentheses or brackets help clarify precedence. Logic gates, their symbols and truth tables. Logic operators and, or, and not are implemented using logic gates, which in turn are implemented using transistors, as we have discussed earlier in our course introduction slides. This is the symbol for AND gate, and here is the truth table for the AND gate. This is the AND gate with two inputs, X and Y, and this is the output X dot Y. The truth table has all the outputs for the four possible combinations of inputs that we can have. Note that an AND gate produces 1 and the output only when all its inputs are 1. For all other combination of input values, the value of AND is 0. Here is an emulation of AND operation. This is with some electric circuits. Here we have, say, a bulb or light. We have two switches indicated as X and Y, or controlled by X and Y. And here we have power supply. These two are symbols for ground. In this emulation, when both switches are closed, that means X is equal to 1 and Y is equal to 1, then current flows from here to there and the light is turned on. When any of the switches is off, meaning X or Y is equal to 0, then the current cannot flow and the light is off. Here you see symbol for two input OR gate. The inputs are X and Y, and the output is X plus Y. And the truth table of the OR gate is shown here. OR gate is kind of dual to AND gate we saw in the previous slide. For example, an OR gate produces 0 at the output only when its inputs are all 0. For all other combinations of input values, the output of OR is 1. Here we have symbol for NOT gate. Input is X, output is X prime. The truth table is simple. It has only one input variable, X, and these are the two possible values for X, and the corresponding output is shown here. So now we will see multi-input AND and OR gates. So this is a symbol for n-input AND gate. The inputs are X sub 1, X sub 2, up to X sub n. And the output is X sub 1 dot X sub 2 dot X sub 3 all the way up to dot X sub n. Here we have the corresponding symbol for an n-input OR gate. Again, the inputs are X sub 1, X sub 2, up to X sub n. The output is X sub 1 plus X sub 2, all the way up to plus X sub n. Here is something for yours to do. Write the truth tables for 3-input AND and OR gates. Representations of logic functions. a logic function can be represented in multiple ways. Using an example function, we show three methods here: algebraic, truth table, and semantic. So this is an example of algebraic form of logic function. This function f has three variables, x1, x2, and x3, and the relationship is shown here. So x1 plus x2, and this sum is ended with x sub 3. This shows the truth table representation of the function. These three columns titled x1, x2, x3 have all the possible values that we can have. Since there are three variables and each variable can take only two values, 0 and 1, there are 2 to the power 3 possible inputs in this case. That means 8 combinations. And the rightmost column indicates the value of the function. This diagram shows the schematic representation of the function. Again, there are three input, x1, x2, x3, and this is the output. x1 and x2 go through an OR gate. This corresponds to this plus operation or OR operation. So the output of this OR gate is what we get from this expression in the parenthesis. The result is then ANDed with x sub 3, and that's the output f. Going back to this algebraic expression and comparing this with other representations of the function, we see that algebraic form is quite compact. The truth table explicitly shows all input-output combinations. The schematic form is used in lab 1 of this course. And schematic form is also very close to the physical implementation of circuits. Going from one form to another form is straightforward in majority of the cases considered in this slide. For example, going from algebraic to schematic form is easy. It is also easy to go from algebraic to truth table. But it's not so obvious how to go from truth table form to the algebraic form or from truth table to the schematic form. But we will learn how to go from truth table to other forms later in this course.